So I'm Brian Beal. I work at the University of Maine at Machias and the Downeast Institute, and I'm going to talk today about two studies that were conducted in and around Freeport in northern Casco Bay. The first talk has to do with the 2016 recruitment boxes that Sarah was talking about, and the folks that are the co-authors here. Really, I owe an awful lot of thanks to and help from, because this study, as you'll see in just a moment, was among the big ones that I've done, and I really want to thank them for all their help. We're going to start with a little bit about the biology of soft-shell clams. This few minutes that I'm going to take to talk about clam biology will help us also interpret and understand the next talk that I'll be talking about, which is using crushed clamshells for sediment buffering, because both of them are looking at wild soft-shell clams. So I'm not talking about cultured clams. It doesn't have really anything to do with production at the Downeast Institute. It has to do with what's happening in the wild. So, how do clams get to be clams? Perhaps this is old hat to some of you, but maybe it isn't. Clams are not produced from the adult, and the juveniles settle right next to the adults on the same flap. Okay, so if you're thinking that, that's not the case with mussels, with scallops, with oysters, with razor clams, with soft-shell clams. Okay, they have a way of spawning, and let's see. Do I have a previous here or not?
Sometimes it just arrow up on.
Yeah. So they spawn. There are male and female clams, and there's a particular time of year, usually May to June, but it could be longer, that they're producing their gametes and shooting these into the water column, whether they're males producing sperm or females producing eggs. You hope that spawning is synchronous, that it occurs at the same time. You also hope that you have enough animals in an area so that when the female spawns, that those eggs get fertilized by the sperm that are swimming around. And if you really think about that level, if you don't have enough sperm to fertilize eggs, spawning could be a waste. So it's not like this is, a slam dunk. Once fertilization occurs, it's happening in the water column. And this animal that's now called a trochophore, this thing right here is going to look an awful lot like a mussel or an oyster or a razor clam. In fact, I bet you that there's nobody in this room right now that could tell the difference between an oyster trochophore and a soft-shell clam trochophore. Anyway, they continue to develop and to grow and to grow a shell. And this organism here called the veliger, which is now in its first week of life, is swimming just fine. It has a shell. It's been removed in this picture so that you can see its internal anatomy. But it has everything that it needs. It has a mouth, it has a stomach, it has a heart, it has an anus, it has a little helicopter thing on the top called a velum, and that allows it to run around in the water column up and down. It also helps in feeding. Pretty soon, the biological clock ticks, the shell gets really heavy, the foot gets really, really large compared to the animal, and now this thing is going to do this in the water column, and it's going to go and it's going to test out the sediment. And if it lands on something that's fairly hard, like this top of this podium here, it's going to put its foot in, it's going to shoot its velum out, and it's going to go swimming away. But if this is a soft substrate, something that it might be able to dig into a little bit, then it's going to stay there and remain and quickly undergo a change of shape called metamorphosis, just like caterpillars into butterflies. It's going to change its shape from something that's more quahog-like to something that's more elliptical, like a clam. And so at that metamorphosis stage, these clams are 1/4 of 1 millimeter, or 250 microns, which is about 1/125th of an inch. So we're not talking about an animal that's very large at all. And if I can get this thing to go and load up, oh, there we go. So this is a picture of clam spawning. I'm not sure that it's going to show up well. This is taken at the Downeast Institute by Kyle Pepperman a few years ago. The little white things that you see swimming in the water column are back bunches of eggs that are kind of stuck together with mucus. And so one little tiny white dot that you see there is probably close to 200 or 300 eggs. Okay? You can't see the sperm, although it's all over the water column, and these eggs are being fertilized almost immediately because of, this is in a tank, we've got males and females spawning together, and there we go. And this is what they look like about 20 minutes after fertilization. All right? This is a developing soft-shell clam. It's just divided. It's at the two-cell stage. It's not going to be able to swim at temperatures of about 68 degrees Fahrenheit. It's not going to be able to swim for another 14 to 16 hours. But at the 14 and 16 hour stage, it has developed enough so that it has cilia that allow it to go through the water column. And within a day, it will have a mouth and be able to start feeding. So this is a very, very small animal, 0.002 inches. 10 days later, this veliger larvae, this has a shell. Again, this is a photomicrograph taken under a microscope with, I think, an iPhone, right, Kyle? Yeah, pretty amazing. The little dot that you see in the middle of this veliger is the food that we've been using to feed this clam so that it will grow and be healthy. It's at least 12 or 14 days from being able to settle from the water column. And when that settlement from the water column occurs, this is what those clams are going to look like. This is the quarter of a micron, of a millimeter clam, the ones that are about 1/125th of an inch. And they're probing, they're on a glass slide. You can see the foot moving. This is what's happening all up and down the coast from essentially June through August every year here in Maine. Okay, so the notion then is that these clams come to your flats from the water column, and they're going to be swimming for these 2 to 3 weeks. So put yourself on a mud flat and stay there for 3 weeks and watch the tide come in and out over you. I'll give you a straw so that you can breathe at high tide. So that clam that you're standing right next to spawned 3 weeks ago. Okay, you do the math, but tell me what the probability is that the egg or the eggs that animal produced are going to go away for 3 weeks and find themselves right back there. It's pretty unlikely. Pretty unlikely. So I call this settlement from the water column the salt shaker effect. And there's not a lot that we can do about getting clams up in the water column. And as you'll see, there's more that we can do in terms of enhancing their survival later on. I'm going to be using the word recruitment. And recruitment is a separate event from settlement. In fact, there's settlement from the water column to the benthos or to the bottom. And then there's some period of time after settlement that people like myself are finding clams. In other words, here's a timeline. There's the planktonic phase when they're in the water, and then they settle. And that's an instantaneous process. No one's watching settlement because you can't do it. The only thing that you can do is to find out when the clams recruit, but that's up to you. That is to say, it could be 14 seconds after they settle, or a week after they settle, or a month after they settle, or 6 months after they settle. So after they've settled, they recruit. But there's a time frame that goes by after they've settled. And so let's blow this up just a little bit more and talk about, well, when you find them, it means that there's a period of time that they've been exposed to things on the mud, like milky ribbon worms, like green crabs, like other worms, like fish. And so there's some post-settlement mortality that occurs before we even see them as a recruit, okay? So I'm using recruit as a noun. It's a small clam, and it could be this big or it could be that big, depending on how much time has gone on after it's settled. So what will cause mortality? What's the cause of this post-settlement mortality? Well, there's a whole bunch of different things that it could be. Everything from disease, dissolution, because the mud is really, really acidic. There might not be enough food and it could starve to death. Or it could suffocate if a bunch of green slime came in and settled on the mud. Flipped mud. There's something that you don't think about, but these things are 1/4 of a millimeter. And you're out there digging, and you flip the mud. And lo and behold, you don't know it, but there's clams underneath that. And when you put 1/4 of a millimeter clam underneath 6 inches of mud or 12 inches of mud, guess what? It might die. So there's other things like stress from pollution. Certainly predation. You don't hear much about UV radiation, but these clams are very, very high up in that water column, in the mud. So they're almost at the surface of the mud. And so, maybe there's a problem with UV radiation in terms of post-settlement mortality. Or it could be a combination of these and other factors. So there's a whole bunch of reasons why you're going to get mortality between the time of settlement and the time that you find them as a recruit. Okay, so in April of 2016, with Sarah and Chad and Clint, we went to 20 different sites along the Harrisicot River, and we took core samples at the high and the mid and the low. And we used a regular coffee can core and put each one into a bag that was labeled so that we knew what site we were at, what tidal height we were at. And then we sieved these through a 1 millimeter sieve, pretty small. And our goal was to find clams. Now I'm going to show you a series of, this is just a fake slide, but I want to get your eyes peeled so that when you see green, you think of the high tide mark, at least for a while. When you see this, turquoise, you think of the mid, and black means the low. So I'm going to show you a bunch of slides where this is going on. And I know these are small, but what's the color that you see most often there, John? What color do you see more frequently? Don't tell me you're colorblind. If I pick at random a colorblind, damn! Tell him green. Okay. So you see more green, and the reason why you see more green is because, there's a lot more clams at the upper intertidal than there is at the mid and the low. And that was on the western side of the Harrisicot. Back to you. In fact, this is how much you see. You see about 18 clams per square foot versus about 2 versus about 5. And if we go to the other side of the Harrisicot, well, you see less green, but you see, comparatively speaking, more green than you do any other color, except at this one site way up here at site 20. But for the most part, you're seeing mostly green. And so this is what we find when we look for spat in the springtime. So can you call these recruits? Sure. It's just 8 months has gone by since they settled or whatever. But I want you to take home the message of this pattern. Okay, this is a pattern of high being the most clams, and mid being less, and low generally being less than that. In fact, hardly anything at the low. So remember that pattern. So this is the results then totally of that sampling escapade. And if we compare the west side to the east side, we find that there's actually more spat on the west side than we do the east side. The pattern isn't quite as clear in terms of the relationship between mid and low for each side, but certainly the pattern is clear for low. And that is that it's generally much, much reduced compared to the high. What sizes are those clams? Well, they're fairly small. In fact, about 90% of them are less than 3/4 of an inch. And the average size of the clam, interestingly enough, was larger than that in the mid and the low. Okay, so those are the observations. And that's all these are. Okay, this is a lot of sampling, it's a lot of work, but at the end of the day, all we have is this and a guess. Anytime that you do sampling, because you haven't manipulated anything, you haven't manipulated any variables, all you have is a quantitative observation. That's it. And we can all sit here and chew the fat about what process or what's going on that has resulted in this pattern. Okay? So, my question is, are the patterns the result of settlement or post-settlement processes, or are they a combination of those two? So, what we did then was, what I reported on last year was to use these 1 foot by 2 foot boxes that are made out of strapping, that are lined on the top and the bottom in this figure with pet screen. It's a glorified window screening. It's actually a little bit smaller aperture. It's about a 1.8 to 1.9 millimeter aperture, so it's pretty small, but it's strong. And what we do is we take these boxes and we just put them on the mudflat. And in 2015, on the west side, if you can see this legend, you'll see that most of the boxes had either 0s to 50. On the east side, really something, remarkably different. Most of the boxes had 50 to, in some cases, over 500 on average per box. And it wasn't like we put out 20 boxes here and 20 boxes there. We had, I think last year we had 120 boxes total, 60 on each side of the river. So, using that information, we kind of blew up the design for 2016 to try to figure out a little bit more about this process and that pattern that you saw. So we asked 3 questions in terms of varying spatially, which was, do we still get this east to west difference? Because recall from what I just showed you, there were a lot more clams on the east side. That's the Wolf Neck side, if you're familiar with the geography of Freeport, on the Wolf Neck side than the other shore. So we got the Wolf Neck shore, we got the L.L. Bean store side shore. That's the west side. How about from the mouth of the river to the head? Well, if we put boxes at the mouth and we put them in the head, we put them all the way along, we'll find out some answer to that question. And then, how about, rather than putting them out at one tidal height, which is what we did in the first year, that we put them where we took the core samples. We put them at the high, we put them at the mid, we put them at the low. In addition, we asked, what's the effect of different sizes of netting, the holes in the netting, the aperture size? So we used things like pet screen, and you'll see in just a moment we used a mesh that's 1/8 of an inch and a mesh that's 1/6 of an inch. So our experimental design was to put boxes on both the east and the west side. The 1 foot by 2 foot boxes comprised of pet screen, the 1/8 inch screen, the 1/6 inch screen, and then we had controls. No screen at all, just open boxes. I won't get into that, but anyway, 10 locations on each side of the river. That gave us 20 locations, and then the 3 tidal heights. So if you do all that math, and we included for each tidal height 2 what we call blocks. And in each block there's 2 pet screen boxes. In each block there's 2 1/8 inch boxes. In each block there's 2 1/6 box, and then there's only 2 opens, because I didn't want to go the full route on that one. The bottom of every box has pet screen on it. The bottom has pet screen. The top is what varies. okay? So there's 14 boxes sitting out on the mud flat at each tidal height, at each of the 10 sites on one side and each of the 10 sites on the other. So if you looked at this from above, this is one site. There's 14 times 3 or 42 boxes at each site. Times 10 means there's 420 boxes on one side of the river and 420 boxes on the other side of the river. And so that's the experimental design. I hope you're tired because I know that I am. So this is just an overview of what it looked like just getting all this stuff from DEI to Freeport and then deploying it. It took an awful lot of time and a lot of organization and a lot of help. And so this is one of the sites that we did. This is putting in the first block in the upper intertidal, and that's what those 7 boxes in block 1 would look like. And then we had 840 minus 7 left to go. We anchored these boxes by taking laths and shoving them or pounding them down in the mud right next to the end of the box. And once that lath got to the height of the box, we took trap nails and nailed the lath to the box. And that was an excellent anchor. And I can say that because when you put out 840 of anything in April, and then you walk away and you don't go back until November, and you find 840 at the end of the day, it's a good anchoring system. And it's also very appreciative of people staying the hell out. So in November, we went back and we hauled all the boxes off the mud flats. And not all of them looked like this. In fact, some boxes had no mud in them, and some boxes were filled with mud. Some boxes had lots of clams, and other boxes had nothing. But this is what the boxes looked like coming off the flats. And this took us weeks to do. Not, chunks of days like 21 days in a row, but, Thursday to Sunday, Thursday to Sunday, Thursday to Sunday. Because I have a half-time teaching appointment, so I'm coming to the classroom, right, Katie?
Yeah.
Nice to see you.
Me too.
So what do? Well, we need to process the box, which means we need to scoop out all of the mud from the box, or take a spatula and try to get the mud out. But to remove all of the sediment from the box, and then to put that sediment, thanks to Jim and Lashea here, through a 1 millimeter sieve, and then take all the clams and put them in a plastic bag with the label that tells us the block, the site, the tidal height, and the treatment, and then freeze them. Take them back to DEI and ask Kyle and Cody to please stand up. And ask Kyle and Cody to please stand up. Yes! Because between around December 10th, when they started to take these things out of the freezer at DEI, all 840 of these bags, and count every clam that was in every plastic bag from every one of the boxes, and to measure a subset of those clams. They got done around the 20th of February. And I put this talk together because they were able to achieve the goal that I set for them, because I knew that it would take me a week or so to put this talk together. So there it is. This is hot off the press. So how do we get this to move? I guess we are supposed to click there or do that. But not now. Oh, okay. So what I wanted to show here, you see the red circles? Oops, there's one more red circle. So take a look at the sizes of the clams that we get in these boxes. I should have remembered, but what I wanted to show you was, look at how big this clam is. Turns out that clam is about 25 to 30 millimeters. Look at how big this clam is over here. It's about 3/4 of an inch. This clam right here is less than half an inch, and this clam here is about 3 millimeters, or about 1/8 of an inch, all in the same box. All in the same box. And we also find other things, which is really cool. We find everything from razor clams to false angel wings to bloodworms and sandworms to hard clams and oysters. I'm talking about soft-shell clams today. And so when they come back from Freeport and go into a freezer, and then Cody and Kyle and others at DEI start to help process them, this is what they're looking at. And that's what the data looks like. Oh yes, I forgot to tell you. In addition to soft-shell clams and all the other interesting bivalves and worms, we also find green crabs. What did Sarah say? Oh, the green crabs haven't gone away. All right, I remember you saying that. So this just gives us an idea of how much sediment was in these 840 boxes. And you can see something interesting, and that is that at least at the upper intertidal, and both for east and west, there's more mud in the upper intertidal boxes. There's a little more mud in the mid-intertidal boxes, and it doesn't make any difference where the box was put out. There's as much mud in the box, and this is an average that's just about a quarter of an inch below the top of the box. Okay. If we look at the amount of sediment in the box as a function of the treatment, we find that there's no difference between pet screen boxes and 6-inch boxes, but the open controls have a little bit less mud in them than the boxes do. So we also took core samples at the same time we removed the boxes, and the pattern that we found in the core samples adjacent to the boxes was very similar in November as it was in April. Okay, so we see that same pattern again. And the sizes of the clams, well, about 88%, 78 to 88% were less than 3/4 of an inch, just like what we found in April, pretty much. And the average clam size, once again, was larger in the upper zone than it was the smaller zone. Here's the data for the west side. And what do you see? You see mostly yellow and green, which is just about what we found in the first year when we only did this at one tidal height. There's not a really good and consistent pattern here, but one of the things that is a pattern mostly is that you see yellow in the low, yellow meaning fewer clams. You see green in the mid and the upper, more so than you do anywhere else. Let's take a look at the recruitment boxes. And so I've used the same scale on this axis here as I have here. This is the number of SPAC, or number of recruits per box. So the first thing that you should see is that the bars at the high are not as tall as the bars at the mid and the low. Okay, so that means that we found more clams in the boxes at the upper and fewer at the mid and fewer at the intertidal, the lower. What I have arrayed here is what we found in the pet screen box at the high, the 1/8-inch box, the 6-inch box, the open box. Yes, clams survived in the open box, and it turned out that it wasn't much different than what we found in the controls. Let's take a look at all of the sites together, and that is that there's not a lot of difference between open boxes and protected boxes. What's going on? And there's not a lot of difference between even what's in the cores. And if you look at this axis, the number of SPAC per square foot is only around 8, is the highest one. That's not very much. Well, green crabs. That's going to be the theme of what I'm talking about from here on in. Because take a look at the number of green crabs that were found in these recruitment boxes in November. A total on the west side only of 1,008 out of 420 boxes. If you do the percentages, almost 90% of all the boxes with protective screen on them had green crabs in them. where the hell did the green crabs come from? Well, green crabs, turns out that they're settling on flats in August, September, October. They're not growing an awful lot. And by April, when we're putting the boxes out, these little green crabs are even crawling through PET screening, 1.9 millimeters. You don't even see them. They're also crawling into the 1/8" screen. They're also crawling into the 1/6" screen. We found fewer green crabs in the open boxes than we did the protected boxes, because what happens is they get into those protected boxes, don't they? And they feed. And then what happens? They grow, and they shed, and now they're trapped. And what they're getting is a rain of settlers, the salt shaker effect. And that salt shaker effect is really doing a great job feeding these green crabs. So remember the recruitment boxes? Well, this is how many total green crabs were found across the treatments. Quite a few. Now, because of the great work that these guys did in processing the data, I can take a look at the data from a couple of different angles. And one of the angles was, what would happen if I looked at just those boxes that had crabs in them versus those that didn't? Or what would happen if I looked at boxes where they didn't have big crabs, but just little crabs? When I say big crabs, I'm talking about 20 millimeters, which is just a little bit less than an inch. It's about 3/4 of an inch. So here's what we found in the boxes that had just only green crab, without the green crabs that were large. And it turns out that there's still green crabs in these boxes, but when I compare the boxes without those large green crabs to the boxes with all the crabs in them, that the clam numbers doubled in the boxes without the large green crabs. If I only look at the boxes with green crabs, look at how lousy the numbers are. Okay? So, in terms of the relationship between the number of green crabs that are greater than 20 millimeters per box, you know, when you don't have any, you have a lot more clams in these boxes. So this is, again, with all the data put together, and this is the boxes without the crabs. And again, that amount of the bar above the red is how much you get when you remove those crabs. How big were the clams? Well, they were smaller than 1/2 inch in most instances. The largest recruits, let me go back. So one of the things that I had the guys do was to say, okay, you're going to take samples from these bags, which were the boxes. And I want you to go in and take a random sample of clams and measure 20 of those clams. But I want you to do one thing for me. If you see that your random sample didn't contain the smallest clam, then I want you to take the smallest clam from the sample and measure it. Just put it on the data sheet. So here's the distribution of the small clams. So this is 2 millimeters, 4 millimeters, 6, 8, 10. 12 millimeters is 1/2 inch. So as you can see, almost every clam that was the smallest in each sample was from the boxes in the upper, again with the mid, and they're a little bit larger at the low. And I also said, if your sample didn't contain the largest clam, take that one out and measure it. And this actually blows me away, is because two things. One, there weren't any largest clams larger than an inch from the upper boxes. But if you look at the lower boxes, there's a large percentage of clams that are actually greater than an inch and a quarter. Think of it. Clams that settle in a box on a mudflat reach an inch and a quarter or larger between April and November. That's phenomenal growth. Phenomenal growth. We need to take advantage of it. So is there any relationship between the amount of sediment and the number of clams? No, there wasn't. So to summarize on the west here, we have no consistent patterns from the mouth to the head. The average number of clams is around 10 per box, which is about 1 clam per square foot. The maximum number of clams that we found per box is 290. There were more recruits in the upper and mid versus the lower. When you look at it with all boxes considered, there wasn't any difference between the pet screen and the other ones. We found over 1,000 green crabs that ranged as great as almost 2 inches, some of those green crabs. Recruits were twice as numerous in the netted boxes when the crabs greater than 20 weren't there. Greater than 60% of the smallest clams were less than ½ an inch. The largest clams were 0%, 20%, and 60% were greater than an inch depending upon tidal height. And there wasn't any relationship between the amount of sediment that fell and were collected in the box versus what we ended up with in terms of recruits. Here's the east side. That pattern is completely different than it was on the west. Completely different. And there's one thing that's consistent, though, that there's a lot of yellows at the low. So I should have done this. This is the high, this is the mid, this is the low. Okay, and this is an average of all the 14 boxes. So it even includes the controls. But take a look at these big bulking, 200 to 500 on average per box, 50 to 100 on average, 100 to 200. So once again, there's more settlement going on that side of the river. And I will go through these much more quickly now that you're used to seeing these bars. But you see a pattern. And the pattern is that there's more clams settling or recruiting in the upper than there is at the mid and the low. This is the treatments, and we actually found more clams in the 1/8-inch netting, but look at the y-axis or the perpendicular axis that tells you the average number. We were down by the value around 8 to 10 across the river, and on this side we're 35, 75, 50, and in the open less than 20, and the cores are less than 10. But green crabs were there as well. It's not that they weren't, there just were fewer of them, 641 compared to 1,000. And rather than 90% of the boxes containing green crabs, 70 to 80% of the boxes contain green crabs. And looking at boxes with and without the largest crabs, there was about a 25% increase in the number of clams in boxes without the largest crabs. So that line from the red up tells you the increase in production outside of boxes that had the big clams. The same kind of pattern with the sizes. Most of those sizes were less than an inch. And again, there's still a lot of clams that are in that 1 1/4 inch and larger size range. In fact, we got a clam that was 47 millimeters. A 2-inch clam is 50.2 millimeters. So the summary, a pattern of relatively high recruitment at a few of the sites, and that was similar to what we found in 2015. Rather than 10 clams per box, the average was 74. More recruits were found in the upper versus the mid and the lower. Higher recruitments occurred in boxes with the largest mesh. The pet screen didn't give us the largest number. 641 green crabs ranging in size up to about 40 millimeters. Recruits were 25% more numerous. 60% or greater were less than ½ an inch. And the pattern was pretty much the same as we found for the largest clams per box. And once again, no relationship with sediment. So this is the result, east versus west, everything combined by tidal height. And that pattern looks an awful lot like the stat core sampling. And these are the patterns that we find as a function of the mesh on the top. So I think the results from both 2015 and 2016 showed fairly clearly that there's a reason for the lack of high densities of commercial-sized clams in the Harrisecret River at these sites. and it's not due to disease, and it's not due to ocean acidification. If there were, these clams would have dissolved before they got in the boxes or afterwards. It's not because of overharvesting. It's not because there's a lack of spawning stock. It's not because there's no clams settling into the boxes. It's not coastal pollution. It's not loss of habitat. It's not that the mud is unproductive. It's not green slime. And it ain't sharks! Thank you very much.